Hello everyone, myself Soumya VG, Assistant Professor, Department of ECE SJBIT. In this session, I will be discussing about the Module 3 topics of Microwave and Antenna subject. This session is dedicated to Antenna Basics. In the Antenna Basics, the topics that are to be discussed are radiation mechanism, basic antenna parameters like radiation patterns, beam area and efficiency, radiation power density and intensity, beam width, directivity and gain, antenna apertures, effective height, the radio communication link, and finally antenna field zones. Let us first understand what is the meaning of antenna. The antenna is an element or a component of the radio frequency system. It is basically used to release the radio frequency energy or to pick up the radio frequency energy. In short, I can define the antenna as a component of the radio frequency system which can be used to do the transmission of the radio frequency energy or reception of the radio frequency energy. And what type of device is this? This device is usually made up of a metal, so it is a metallic device, and it accentuates the radiation energy in a particular direction or in some direction, and it also optimizes the energy transfer. So an antenna is an element which is basically used to transmit or receive the radio frequency energy, and it can be a metallic device and it optimizes the energy transfer. Now let us know what is the IEEE standard definition for the antenna. In IEEE standard definition, the antenna is defined as a metallic device for radiating or receiving the radio waves. The antenna is a metallic device for radiating or receiving the radio waves. Okay, in the transmitter section, we have the component like this, and in the receiving section, we have a component like this, and this is the transmission of the electromagnetic wave or the radio frequency wave. From the source that is from the transmitter section, this is the component that is actually representing the source, and this horizontal line represents the guiding of that signal in this path which is made up of a metallic device again, and in such a case the signal will be called as a standing wave. And from that we have got this extension, okay, and this extension actually represents the conversion of this standing wave to the radiated free space wave. And again at the receiver section, we have the antenna part which actually takes this free space wave and it converts that to the standing wave, and finally it will be sent to the receiver section. This figure represents the Thevenin's line equivalent circuit of antenna in the transmitting mode. In the source section, that is in the transmitter mode, in the source section, we have got the source with the supply represented as Vg with the source impedance Zg, and at the in the transmission section, after the source we have got the transmission line in which we are having the standing waves, and this transmission line has got impedance equal to RL plus RR plus JXA, and after that whatever the part that is actually converting that to the radio frequency wave has got a resistance RL as well as the resistance RR with the impedance XA. This actually we call it as antenna because this is the one which is actually converting the signal to the electromagnetic wave or the free space wave, or we can tell that this is the section which is actually converting the electrical signal to the electromagnetic signal. Now in this diagram, the RL is representing the conductor and dielectric losses, RR is representing the radiation resistance, and XA is representing the imaginary part of the impedance. The imaginary part of the impedance is represented as XA. Now, as we know, the James Clerk Maxwell is the one who is actually predicted the existence of the electromagnetic waves in 1864. And between 1885 and 1889, a professor of physics at Karlsruhe Polytechnic, he produced electromagnetic waves in the laboratory and measured their wavelength and velocity. These are the equations of the Maxwell that are being proposed with respect to the electromagnetic waves. Let us first know the history of the antenna. Who is the person who actually found out the first antenna? The first antenna was actually built by German physicist Heinrich Hertz. The first antenna was built by Heinrich Hertz. He was a German physicist and he built the dipole antenna in 1888, and this was the picture of that dipole antenna. Now, later in 1895, the first antenna application on transmission signal was found. It was found over 2.8 km, and this was done by the Italian investor named Guglielmo Marconi. He was the person who used this first antenna application on the transmission signal over 2.8 km in 1895. Now, after this, in 1920, the Hage-Huda antenna was built. Next, in 1939, horn antennas. In 1940s, antenna arrays. Again in 1940s, parabolic reflectors as well. In 1970s, patch antennas, and in 1980s, PIFA antennas were actually built. This slide gives the representation of the different types of antennas, how these antennas actually look like. This is the first one is actually the diagram of the wire antennas. This is the microstrip antennas which we actually found in our mobiles. Next, this is the reflector antennas which we actually found in our dish TVs. Next is the aperture antennas. Then we have log periodic dipole array antenna. Log periodic dipole array antenna. Let us learn each antenna one by one, starting with the wire antennas, where these antennas are being used, what are the applications. The wire antennas, again they are of three types. One is the dipole antenna, which is having two poles here, and the wire which is been bent in the form of a circle, we call it as circular loop, or if it is bent in the form of a square, it is called as square loop. And if the wire is been bent in the form of a helix, that results in helix antenna or helical antenna. And these wire antennas are mainly seen on automobiles, buildings, and in ships, aircraft, as well as in spacecraft applications. Next, we have aperture antennas. In aperture antennas, again we have pyramidal horn, where we have got restoration in the form of a pyramid shape, which is called as pyramidal horn antenna, and if this is in the form of cone, it is called as conical horn antenna, and one is rectangular waveguide antenna. And this aperture antennas, as the name tells, aperture means this is actually representing the area which is actually used for converting the electrical signal to the electromagnetic signal. By this actually these antennas are being named as aperture antennas, and these aperture antennas are actually used at high frequencies, and they are useful for aircraft as well as spacecraft applications. Next, we have microstrip antennas. This is the microstrip antennas. In the microstrip antennas, we can have the rectangular microstrip antenna or the circular microstrip antenna. It means whatever part that is being present on the substrate, this is the metallic part, this is being present on the substrate, and on the other hand we have got a ground plane. and on the other end we have got a ground plane. And if this metallic device, if it is in the form of a rectangle, we call this as rectangular patch antenna, or if this metallic device is in the form of a circle, we call it as circular patch antenna. And these are the antennas which are actually used in our mobile phones. And coming to these microstrip antennas, they are actually very light weight as well as a low volume, that is why they are used in mobiles. And low profile planar configuration is there in this, which can be easily made conformal to the host surface. And for this antenna, the fabrication cost is very low, therefore it can be manufactured in large quantities. And coming to the polarization, it supports both linear as well as circular polarization, and they can also be integrated with the microwave integrated circuits as well. And coming to the frequency operations, they are capable of dual as well as triple frequency operations, and whenever they are mounted on rigid surfaces, they are mechanically robust. These are the we can call it as characteristics of the microstrip antennas. The first one is they are having lightweight and low volume, and low profile planar configuration, which can be easily made conformal to the host surface, and they have got low fabrication cost and hence can be manufactured in large quantities. They support both linear as well as circular polarization. They can be easily integrated with microwave integrated circuits. They are capable of dual and triple frequency operations, and they are mechanically robust when mounted on the rigid surfaces. Coming to the applications, they have got applications in satellite area, they are used in microwave area for communication, in cell phone antennas, in GPS antennas, as well as in RFID applications. These antennas are being used. Next we have array antennas. This is the example of array antenna, the Agee-Woda array. In the Agee-Woda array, we have got reflectors, the feeder element, which is the driven element, which is actually generates the signal, and then we have got directors. Since this is arranged in the form of a array, we call this as array antenna, and this is named by the person who invented this antenna. The both persons are Agee and Woda, so this antenna is named by them. And next is the aperture array. If the aperture antennas are been arranged in the form of the array, this becomes aperture array antenna. Similarly, microstrip patch array. Whenever the microstrip patch antenna is been again arranged in the form of a array, the patch is been arranged in the form of a array, we call it as microstrip patch array. And again the waveguide. Whenever we have got slotted waveguide array in this fashion, we call this as slotted waveguide array antenna. And coming to this array antenna, why they are actually used is in order to get the maximum radiation in one direction and to get the minimum radiation in the other direction. Whenever we want the maximum radiation in a single direction, we go for this array antennas, and in that case we will get the minimum radiation in the other direction. Next we have reflector antennas. The first one is a parabolic reflector with the front feed. This is actually, the reflector is actually forming a parabolic shape, that is why this is called as parabolic reflector. This is the feeder element. From the feeder element, the signal will be generated and it will fall on this reflector and it will be reflected, and the reflected waves, it follows the same direction in this fashion. Whenever we want to transmit the signal for many kilometers or many miles, I can tell, in such case we go for this reflector antennas. Similarly, there is one more type, we call it as parabolic reflector with Cassegrain feed. In this way, instead of one reflector, we will be having two reflectors here. This is where the feeder element will be fed. From this, the signal will be reflected, it will be sent to the subreflector first. From the subreflector, the signal will be reflected to the reflector, and then it will follow the single direction for the transmission. Next we have corner reflector. In the corner reflector, we have got a feeder element in the middle, and this signal will be actually sent to the corners of this reflector, and it will be reflected and follow the same maximum direction of the transmission. And these reflectors antennas are being used to send the signals, in which case they need to travel millions of miles, and they have got diameters of 300 meters in order to achieve the eye gain. Next we have got lens antennas. In the lens antennas, we have got the case in which the lens antennas with index of refraction n is greater than 1, and we have got another case in which the index of refraction n is less than 1. When index of refraction n is greater than 1, we have got convex plane, we have got convex convex plane, we have got convex concave plane. And whenever the index of refraction is less than 1, we have got concave plane, concave concave plane, and concave convex plane. And this lens, basically they collect the incident divergent energy in order to prevent it from spreading in undesired directions. We don't want the signal to spread in the undesired directions. In such a case, these lens antennas, what they will do is they will collect this incident divergent energy together at one point, and they can transform various forms of divergent energy and into plane waves. Whatever divergent energy they have collected, they will transform that different forms of divergent energy into the plane waves, and they are basically used at high frequencies, and they will be geometrically configured with respect to the choice of materials. Whatever materials we use, depending on the choice of materials, they are geometrically configured. This is the slide in which the world's largest single radio telescope, which is having a 304.8 meter spherical reflector, is being shown. And this was actually present in National Astronomy and Ionosphere Center in USA. And this is the world's largest single radio telescope. Now let us know what will be the gain and bandwidth, beamwidth of different types of antennas, whatever we discussed now. It has got three columns. One is we have got type of antenna, and one is we have got gain in decibels, and then we have got beamwidth. If I take an isotropic antenna, the gain will be 0 because it radiates in all the directions, and the beamwidth will be 360 into 360. If I go for off-wave dipole, the gain will be 2, and the beamwidth is 360 into 120. And if I go for LX 10 turns antenna, the gain is 14, and the beamwidth is 35 into 35. And if I go for small dish, the gain is 16, and the beamwidth is 30 into 30. And for large dish, the gain is 45, and the beamwidth is 10 into 10. Now let us see what are the applications of antennas where actually we use these antennas. Antennas are used in systems such as radio and television broadcasting. They are used for point-to-point radio communication, in wireless LAN, in radar and space exploration. Antennas are mostly utilized in air as well as outer space, but they can also be operated under water or even through soil and rock at certain frequencies for short distances. Coming to the antenna applications, they are used in radio telescope, they are used in satellite communication systems and television, they are used for radio and television, for radar, in mobile phone, Bluetooth, Wi-Fi and WiMAX, in global navigation satellite systems such as GPS, in wireless sensor network, in radio frequency identification system, that is RFID. Like this, the antenna is used in almost all the fields, starting from the common general applications like mobile phone, Bluetooth, Wi-Fi, WiMAX, RFID, to the radio and astronomy applications as well, in GPS applications as well. Now let us know what is the radiation mechanism in the antennas. This is the picture which is actually representing our source with the standing waves, and finally the signals which are being converted into the electromagnetic waves. Usually all the incident energy must be reflected back whenever there is an open circuit, but usually practically what happens is a small portion of the electromagnetic energy, it will escape from the system, and that it will then gets radiated. What the reason for this is the line of force, it will not undergo complete phase reversals, and some of the wave it will escape. and this amount of escaped energy, it is be very small value. Why it is very small is because there will be a mismatch between the transmission line as well as the surrounding space. This is our transmission line and this is the surrounding space. There is always a mismatch between this transmission line and the surrounding space. So, this amount of escaped energy will be very small. And also, since two wires are too close to each other, the radiation from one tip will cancel radiation from the other tip, because they will be of opposite polarities and distance between them is too small as compared to the wavelength. So, the radiation from one tip will cancel radiation from the other tip. So, finally, to increase the amount of radiated power, we need to enlarge this open circuit. This open circuit has to be enlarged. And in order to enlarge this open circuit, what actually we are doing is, we are whatever wires we are using, that wires will be spreaded on both the sides. Due to this arrangement, the coupling between the transmission line and free space will be improved. Whatever coupling mismatch we are telling between the transmission line and the free space, that coupling will be actually improved. And also whatever amount of signal that is been cancelled will also get reduced. And the radiation efficiency will increase further if two conductors of transmission line are bent, so as to bring them in same line. The radiation efficiency can be increased further if the two conductors of transmission line are bent, so that they will be brought in the same line. In this session we discussed what is antenna, what are the applications of antennas, how actually radiation takes place through the help of the antenna. Thank you.